So in the previous lecture, we talked about continuity. We understood that when a function is considered to be continuous, it is continuous A if the value of that function for that particular input is defined, if the limit at that particular input exists, and if the limit approaching to that input for that function has got the value of the function for that input. Welcome to the lecture 2.3 Mathematics 2.0. In this particular lecture, we are going to talk about discontinuity. We have already seen a continuous function. Now we are going to look to that how, if the function is not continuous, what is going to be treated as discontinuity in that function. What types of discontinuities are available? There can be a discontinuity like this, there can be a discontinuity like this, and there can be a discontinuity where the value at that particular input goes to infinity. So in the previous lecture we said that for a function to be continuous, we need to have three basic things. It should qualify to three basic things. The very first is the function at input A, the value of the function at input A is defined. The second is that limit, we all know now this word, limit when the input or x is approaching to A for this particular function exists. And the third and the most important thing is that limit when this x or the input is approaching to A for this particular function is equal to the value of that particular function at that point A. Try to understand these two things, that when the x or the input is approaching to the A, the value of this particular function is becoming to the value of the function at that particular point. It means this is the depiction of a function which is continuous, which can be drawn in similar fashion without removing the pen, and it is continuous. If I approach to this particular point A either from the left hand side or from the right hand side, the limit exists. The FA, the output of this function, FA is defined. This we know is the output and this we know is the input. It is defined, number one. Number two, the limit both from approaching the left and the right exist, and the value of this limit at this particular point is the value of the function at A. Now let us basically look to a scenario. Say for example, this is the graph of a function. We all know that on the horizontal line we have the input and on the vertical line we have got the output. Say for example, the function is defined in such a way. Now see, look to this behavior of the function. Say for example, this particular plot is given for the height of maybe a missile or a rocket or an airplane, and this is the height side with respect to time. Now this is the time side. Now look, here it is continuous, here it is continuous, but at this point of time, this particular point of time, what is happening is the output given by the sensor is this, but actually it has to be somewhat here, and it is not here. Look to this particular area, and this is nothing but depicting the discontinuity. Now this is very, very important. Very, very important, because at this particular point of time, if we go by the change, by the behavior of the change, it should be here, but it is giving like this. This can be because of the sensor malfunction. The sensor has done some malfunction. Let us look to a scenario that at this particular point, maybe at time t1, the desired output is H1, but the sensor has given the desired output as H2. So the value of the function at T1 has to be H1, but the sensor has given it to H2. Now this scenario is nothing but giving rise to discontinuity. Another scenario, another situation can be in such a way that this is the input side and this is the output side. Let me draw another scenario. Now accordingly, if this is the behavior of the function, now at this particular point, maybe A, what is happening is that if you approach from the left hand side, the value given is maybe say M. But when you approach from the right hand side, the value reached is N. Means this M is nothing but the value of the function at A, and this N is also the value of the function at A. Now this again is a clear-cut form of discontinuity. Another form of discontinuity is that, say for example, the function is 1 by x. Now say for example, the function f(x) is nothing but equal to 1 by x. When it is approaching 0, the value of the function, when it is at 0, the value of the function is what? Getting infinite, because 1 by 0 is equal to the infinity. So this is again in terms of what? Discontinuity. Now these are three basic types of discontinuities. One is, this is known as the removable discontinuity. This can be removed. I'll show you in one of the examples that how this can be removed. The second one is known as the jump discontinuity, because there is a jump in here. This becomes the jump discontinuity. Another example of this jump discontinuity is a function called Heaviside function. Now this Heaviside function is depicted in such a way that this, say for example, h at t. Now this is the output, this is the function, this is the output. So h at any given point of time t for given t is in such a way that this is equal to 0 when time is less than 0, and it is equal to 1 when time is greater than or equal to 0. So at 0 it is 0, but after 0 it takes 1 as a value. Now this Heaviside function, again it is somewhat similar to this scenario, similar to this scenario. And this Heaviside function, I can cite this Heaviside function in such a way that when you switch on the electricity, when you switch on the thing and the bulb starts glowing, it is nothing but depicted by this Heaviside function. And this, at this particular point of time, when x is equal to 0 or t is equal to 0, the value is 0 and t is equal to 0, greater than equal to is there. So at this point of time there will be two values giving rise to the discontinuity. This discontinuity, removable, can be removed at any given point of time. I'll put up an example related to this. Now let us consider that there is a function f(x) given by the steps, that is x square minus x minus 2 divided by x minus 2 if x is not equal to 2, and it is 1 if x is equal to 2. Now if I draw the table as we were already drawing, this is the input value and this is the function's value based upon this particular behavior of the function. If it is say minus 1, then if you calculate, because it is not equal to 2, so you'll have to calculate putting up x as minus 1 over here. This will become 1, this will become minus 1, so plus 1, minus 1, minus 1, 1, minus 1, and so on and so forth. The value is going to be 0. At 0, if you put 0 out here, 0, 0, so this is minus 2, 0 and minus 2, so this is going to be 1, and if it is 1, the value of the function is going to be 2. Now look, if I look to 2, then by virtue of this behavior of the function, it is going to give me a particular value, but because there is a restriction, there is a behavior of the function that at the value 2, it has to have an output 1. Let us look to a scenario. When limit x is approaching to 2, we are looking to this particular scenario. When x is approaching to 2, if I have to evaluate x square minus x minus 2 divided by x minus 2, this is the function. If we all know we can factorize this. I told you earlier also that it can be done using factorization. Simplification can be done using factorization. Otherwise, if you directly put 2 over here, it'll be division by 0. So it can be factorized in x minus 2 and x plus 1, this whole divided by x minus 2. Now this x minus 2 and x minus 2 gets cancelled, so this becomes equals to limit. When x is approaching to 2, this whole function can be summed up to x plus 1, and then this comes out to be 3. Now look to this scenario. The definition of the function says that if x is equal to 2, the value is 1, but when we are putting up the limits, it is saying 3. So there is a mismatch. Now this is something similar, that the value actually is something else and the limit is making it something else. This can be removed in such a way that if I can take it up as 3 or 1, the discontinuity can be removed. So in the coming lecture, we are going to discuss one very important theorem of calculus, that is intermediate value theorem. This is shortly known as IVT. Look to this profile of the ball. Now when the ball is moving from this point to this point, from start to the end, we can easily profile the change. And you know what happens is, it says that if there are 2 points of change, the start point and the end point, there will always lie a point in between which will have the value in between these 2 changes. Maybe something that if I start from this particular point and go to this particular point, it's difficult to visualize right now. But the only thing, the intermediate value theorem clearly states and signifies that if there is a change which is being looked upon in a closed window, there will be an intermediate point which can be defined in the range values as well. I'll try to explain you in a better form in the next lecture. See you then. Thank you.